Okay, a few typical applications of quadratic functions. We've recently seen the case of 200 feet of fence along a river. We want to enclose the maximum possible area. Demand function, we have x is the number of things demanded, and 5,000 minus 2p is, well, x is 5,000 minus 2p, where p is the price. The higher the price you put on it, the fewer are going to be demanded. Cost of manufacturing p things, or buying them or whatever, is $2,000 plus 0.75p. If you're manufacturing, you got to set up your equipment. That might cost you $2,000, and then you might be able to produce these things for 75 cents a piece. So that's a fairly important idea, especially if you're in a business curriculum. But the whole concept applies in many disciplines in unexpected ways. Okay, or projectile path. If the height y of a projectile is a quadratic function, how do you find the maximum height, and how do you figure out where the projectile lands? So let's just quickly look at these. If you've got 2,000 feet of fence, you say, okay, I don't know what dimensions to put on this thing, but I'm going to put one dimension here. I'm going to say this side is x. Now this is implicitly rectangular, and the river runs parallel to this side of the fence. And you know it's a river because there are shark's fins there, and the animals don't want to go in. They just don't find sharks all that tasty. Okay, so we have this situation. So if you choose to do this much fence here, x of it, then you're going to have to use x amount here. So you're going to have 2,000 minus x here. And that'll all add up, obviously. 2,000 minus 2x, I did that before. 2,000 minus 2x. And that all adds up to 2,000. So the area, and that's what we're trying to maximize, is length times width equals 2,000 minus 2x times x, which equals negative 2x squared plus 2,000, 2,000x. Okay? Well, where does this maximize? Well, this is a quadratic function. Vertex is at x equals 500. So we can sketch a graph of this thing. Now obviously if x is 0, we've got 0 area, because we're just running the whole fence along the river, we're not closing anything. If x equals 1,000, then 2,000 minus 2x is 0. So we have these 2 points on the graph, and since those are the zeros, of course, we know the vertex is halfway between, but we also know that from the quadratic formula in a way that I certainly hope you understand. So if the graph looks like this, not lining things up here, here's your maximum area. It occurs for x equals 500. And to get the area, you just plug it back into here. 500 squared is 2,500. Yeah, and negative 2 times that's 5,000. But 2,000 times 500 is 100,000, is a million. No, I didn't square, okay. Square 500, I did that wrong. It's 25,000. No, it's 250,000, okay? And negative 2 times that is 500,000, and 2,000 times 500 is a million, so your maximum area $500,000 if x equals 500. because that's going to give you 500 by 1,000, which is another way to get it. You just see that. That would give you. Okay, so anyhow, you work that out. Now, if you got this, then your revenue equals what I want to say about this. It's how much you get for every one, which is P, multiplied by how many you sell, which is X. And that's 5,000 minus 2P times P, which is 5,000P minus 2P squared. And we could figure out what P would have to be to maximize the revenue. Of course, what we really want to maximize is profit. And that's going to be your, well, let's do it this way, negative 2P squared plus 5,000P minus 2,000 plus 0.75P. Well, that's a quadratic function. It opens downward because you have a negative in front of the p squared, so you find the vertex, and on a graph of profit versus the price you charge. Okay, if you got a projectile path, you got this, you want to find the maximum height, you want to find where it lands. Well, we just can think in terms of the graph of this thing, the maximum height. A is going to have to be negative if it's curving like this. The maximum height is going to occur at the vertex. So you just find the vertex of whatever the parabola is. And where does it land? Well, assuming that y is measured from along an axis here, where y equals 0 at the ground, where does it land? You solve the equation. Ax squared plus bx plus c equals 0. And of course, as you know, this parabola will reach 0 at 2 points. One of your points will probably have might well have a negative value. It'll at least be to the left of where the projectile started, so you probably don't want to use it. And you make the intelligent decision and use the one that applies to the situation, whatever the situation might be.